Do much. Okay, this is lecture 6, operations research. We're going to start off by doing canonical forms today. Anybody have any remembrance of a canonical form that you may have seen? Anybody seen any canonical forms? If you're given some kind of problem, you can convert the problem to a certain form. And you only need to learn how to study that form. Has anybody seen this in any of their classes? Yes?
In differential geometry, you had like canonical frame that you can put a curve in.
Good, differential geometry, canonical frame, excellent. Any other situations where you have canonical form? There's a bunch in linear algebra. When you're trying to solve systems of equations, you might do Gaussian elimination and move your system to an upper triangular matrix. And then you only have to learn how to solve upper triangular matrices, which is pretty easy, you just read up the line. In the old days, people did not like having plus and minus signs in equations. And so when they were solving things like quadratics and whatnot, they would have all the positive stuff on one side and all the negative stuff moved over to the other side. Because they wanted the positives to represent areas or volumes. And you wouldn't have a negative thing.
Just when you're trying to graphic an ellipse on plane,
Mm-hmm.
you want to do this as like a over x over
Sure,
a
you convert it to x over a squared plus y over b squared, or maybe x minus h over a squared, you center it. So you put it into a canonical form so it's easy to work with. And the idea is you then develop a technique that works with that one thing. And you move whatever you have into that form, and then you can just apply your technique. Sometimes it's easier to develop different approaches based on how you have it, because it could be painful to convert. And you must make sure that you convert something before you use it. So one of my favorite whoopsie moments is NASA had a $25 million probe, which became a $25 million crater on Mars. Almost all of the systems in the probe were in the metric, but somehow one subcontractor decided to do something in the English system. So as the probe is descending and it's trying to calculate how much thrust it needs for a safe landing, it miscalibrates or miscalculates because one component is taking measurements in the English system, and the probe ends up crashing on Mars. And you see all these videos, you've got to be very careful that if you're going to put something in a form and use it, that you put it in the proper form. Okay, so let me just start off with some examples. So let's do solving equations. I am not, by any stretch, believing that this is original material, but it's not bad to go back. So let's start off with a linear equation. These are pretty easy. So let's say I have ax equals b. This is not that hard to solve. X equals b over a. And there's lots of different ways you could be writing things. If I had wanted to, I could have written it instead as ax plus b equals 0, and that would go to x equals negative b over a. Let's go to quadratic. We saw earlier in the semester that for a lot of problems, it's easier to study specific forms rather than the general case. And then maybe try to convert something to a nice specific form. What's a nice quadratic to study? Yes? X squared minus a constant. So to try to keep it in the same form, I'll write it as x squared plus b. But of course, it's really not that much harder if I put an a over here. And this would very quickly give us the solution x equals negative b over a, x squared. And then we would get x equals plus or minus the square root of negative b over a. All right, so now that we have this, the more general case is ax squared plus bx plus c equals 0. So the way we want to solve this is, this kind of quadratic is not hard to solve at all. So the goal is, how can we write this like this? Well, we want to write this as maybe a x minus h squared plus k equals 0. Because if we can write it like that, then we immediately get the solution is x is equal to h plus or minus the square root of negative k divided by a. And there's a very famous name for this method. Anybody remember the method? What they call this? You may not have heard of this since 7th grade, 8th grade. completing the square. Let's see. So completing the square. How many of you have seen this method of solving quadratics, completing the square? Okay, did they use that phrase? Okay, so we want to just figure out how should we do this. Well, when we expand this out, we get, a x squared minus 2a hx plus a h squared plus k equals 0. So this tells us if we want this to equal that, negative 2ah has to equal b. So we immediately get that b is equal to negative 2ax, negative 2ah, yes. And now we want ah squared plus k to equal c. So then k would equal c minus a h squared. So hopefully I haven't done an algebra mistake. If I haven't done an algebra mistake, when the dust settles, we then get x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, if I've done the algebra right. But the idea is we took a general quadratic and we reduced it to a simpler quadratic that we knew how to solve. Okay. What about cubics? How many people know the formula for the cubic? How many people know how to find the formula for a cubic? Which would? Google. Wikipedia is also acceptable. Either Google or Wikipedia will quickly generate the formula for the cubic. There's also a formula for the quartic. There is not a formula in general for the quintic and higher, where you have a formula for the roots in terms of the coefficients. Now for the cubic, the way they find the formula for the cubic is they reduce first to a cubic where you have the coefficient of x squared is 0. So they reduce to a very special cubic. And so again, this whole idea of reducing to something simple, reducing to an easier form, it's a fundamental approach. Okay, what we want to do is we want to get to a canonical form. How many of you have taken linear algebra? This is a prereq for the class, I'm just making sure. Good. So in linear algebra, did you do Jordan canonical form? Okay. So I will put review in quotes. There's a lot of material which can either be covered or not covered. It depends on how much time you have in a linear algebra course and what the professor is interested in covering. If I give you a matrix, we often want to understand high powers of a matrix or what the matrix does to something. We want the matrix to be in a nice form. If the matrix, if A is real symmetric, it's diagonalizable. And what this means is we can write A as Q lambda Q transpose, where Q is an orthogonal matrix. Not every matrix is diagonalizable, and this is not the largest class of matrices which is diagonalizable. If A is complex Hermitian, or more generally, if A is normal, it's diagonalizable. We're really not going to care about that in this class, but it's just worth knowing. And so what this is telling us is we can change our coordinate system, and in that new coordinate system, the matrix A is diagonal, and it's very easy to work with. This is what we were talking about when we were looking at ellipses, when we were having the ellipse not aligned with the coordinate axes. We were basically saying, well, let's just lean back like this, and if we lean like this, it's now aligned.
What is this between the keys?
This?
No, between the keys.
Oh, that's a Greek lambda, capital lambda. So I'll draw the lambda very nicely. So this is a capital lambda, this is a lowercase lambda. And then what you typically do is the eigenvalues of the matrix are lambda 1, lambda 2. So we let lambda be the matrix lambda 1, lambda 2, lambda n, and zeros everywhere else. And so since the eigenvalues are denoted by lowercase lambda, we use a capital lambda to just represent the diagonal matrix whose entries are the eigenvalues. Depending on whether or not you want to rotate your point or you want to rotate your coordinates, I always forget which way you want to put the transpose from the Q. Doesn't really matter. Q transpose is the identity matrix. Q transpose Q is the identity matrix. this means Q is orthogonal. And it's a real matrix. And Q is essentially made up of the eigenvectors of A. Okay? Unfortunately, not every matrix is diagonalizable. However, every matrix is upper triangularizable, if that's a word. Upper triangularization. So given A, there exists a unitary U such that U Hermitian is an upper triangular matrix. And again, I might have the H on the wrong side. I guess based on how I'm writing it over there, I'll put the H over here. It doesn't really matter. So I can always put a matrix into upper triangular form. Unfortunately, here I've entered the complex plane. And I may not want to enter the complex plane. So the question becomes, what's the most general form you can do for all matrices? There's something called the Jordan canonical form. I'm not going to go too much into it, but what it says is you can put a matrix into block diagonal form, and all of these blocks, you have lambdas on the main diagonal, you have ones above, and you have zeros everywhere else. We're not going to do that much with this. It's just worth knowing that Jordan canonical form exists. It's possible that the block is 1 by 1, which is the nicest possible case. But it just says every matrix has this form. It can be converted to this form by changing coordinates. So it makes it a little bit easier to study. There's a wonderful problem by John Conway where the solution involves Jordan canonical form. Conway is probably the best mathematician I know at taking the most absurdly ridiculous statement and finding the deepest possible mathematics behind it. So out of curiosity, how many of you have seen the see and say sequence? I've kind of given away the answer by saying it like this. So start off with 1. Can somebody read this out loud? I have 1, 1. Can somebody read the next line out loud? I have 2 1s. Read the next line out loud. 1 2 1 1. 1 1 1 2 2 1s. The amount of deep mathematics behind this is phenomenal. The limiting behavior as to how long each line is relative to the previous involves a matrix which is Jordanizable but not diagonalizable. There's something called the cosmological theorem. There are 92 atoms, 22 is helium. The cosmological theorem says no matter what you start with, I think eventually, from like this, you will have every atom in every line. This is an incredible amount of good mathematics. I will put a link to that in the additional comments today, but it comes down to a Jordanizable matrix that's not diagonalizable. It is not the case that you can always diagonalize. All right. So our goal is to come up with a good form for our problems. And the reason is we can then write a program that will assume the input has a certain structure, and it will analyze it. And again, it's important to be very clear. Sometimes this is not what you want to do. Sometimes it's so painful to convert, it's better to just have a couple of different programs that, look, if my input looks like this, I'm going to analyze it this way. If it looks like this, I'm going to analyze it that way. Theoretically, however, it's really nice to assume that our problem has a given form, so we don't have to break our analysis into cases. So on the implementation side, we may not want to do this, but on the theoretical side, it's very nice and clean. Okay? So canonical form, our linear programming problem. Okay. So we have variables xi, which are greater than or equal to 0. We have the constraint matrix AX equals B, and I think we want to minimize. So I'm going to double check. Yes. And then minimize C transpose X. Okay. Different people have different desires as to how they like to write variables. I like to put arrows over things so I can quickly look down and see that this is a vector and not a number. A lot of textbooks use bold. I really don't want to have to spend a lot of time, going like this. So I will just put an arrow so I can quickly look down and see that this is a vector. You want to be able to quickly look at equations and see what's going on, what's involved. Okay? So what I'm saying is any kind of linear programming problem can be put into this form. Now, for a lot of things, this may not be reasonable. So can somebody give me a situation where an x, yes?
Is CT a matrix, or is that just like a 1 by something vector?
So it's a
It's
one.
just a vector,
It's got to be a vector because it's got an arrow over it.
Right.
So this is actually going to be C1 x1 plus maybe Cn xn. And so this is the key part, is that we're linearizing our objective function. Not all objective functions are linear. We're assuming we have linear constraints. Not all constraints are linear. And we're assuming our variables are non-negative. Not all variables are non-negative. So we have three major assumptions. One of the assumptions is actually very mild and is not harmful at all. The fact that the variables are non-negative. That's trivial to deal with. The fact that the constraints are linear, that's severe. And the fact that the objective function is linear, that's severe. It turns out we can actually generalize and have nonlinear constraints more easily than we can have nonlinear objective functions than we can have nonlinear constraints. So this is the objective function. Now, if you think back to linear algebra, I was talking with a student who's in linear algebra right now, and they were telling me that they're solving systems of equations, and they hate it when the system is underdetermined because there's more solutions, and you have to go through a stronger analysis. So if you left linear algebra with that view, please leave it, and do not bring it to this class ever again. Right? Our goal is to have systems that are underdetermined. Why don't we want an overdetermined or a precisely balanced system?
It has nothing to do with the objective function.
Yeah, nothing to do with your objective function. If it's precisely balanced, we only have one solution. And if we want to try to find the best choice, well, this is the only possible choice. We have no possibility of searching various alternatives and choosing which one is best. We're forced to take something. If it's even worse and it's overdetermined, there might not even be a feasible solution. So you may not even have a way to meet the constraints. So our hope to do something is we want to have a system that's underdetermined, so that we have multiple solutions, multiple feasible solutions. And then we want to look at those feasible solutions and see which one of them is going to be best. Right now, we can only do what is best relative to one objective function, which is linear. Later on, we would like to have multiple objective functions. The problem, of course, is when you have multiple objective functions, how do you deal with, okay, I can minimize this one a little bit more, but at a cost of making this one larger. You need to have some kind of conversion rate. And a lot of people get very upset when mathematicians or economists put numbers on these things, but you need to do that. If you're buying a house, how much do you trade off location to size? A lot of people would much rather have a big house and a long commute to work than a small house and a short commute to work. Where do you care about stuff like that? So can somebody give me an example of a problem where my variables could be negative? So if I'm doing the diet problem, I am not allowed to regurgitate. Okay, I cannot throw up spoo and eat or consume a negative amount of spoo.
Do you have profits and losses of a company?
Sure, so if you try to like profits and losses, or maybe you have buying shares versus selling short. So you could conceivably have a negative amount of something. So having negatives there is not unreasonable. So the question is, how do we handle all of this? So what I want to do is I want to take a general linear programming problem where I have some kind of variables, some kind of constraints, and some kind of objective function. So the general case is I just have variables xi, I have a constraint ax greater than equal to less than equal to b. And what I'll mean by this is each row is either greater than or equal to, or less than equal to b. And then I'll have, I want to minimize C transpose X. Okay, so this is the general form. And I want to show that instead of considering the general form, it suffices to just consider this special form. So let's do, so may assume xi is greater than or equal to 0. Okay? So we're going to show that it's sufficient to assume that the x's are non-negative. An extremely important thing to note right now is just because I'm using the same letters in both statements does not mean the letters are playing the same role. So the x's I use here may not be exactly the same as the x's over here. So when I convert from a general problem to a canonical problem, I may add additional variables. And then you have to ask yourself, is it worth adding these additional variables? Maybe adding these additional variables will make the program run slower in terms of finding the solution, and maybe it would be better to write an algorithm that takes something in that form. That's a different question. Right now, it's just theoretically, it's sufficient to convert everything from a general to a canonical form. And then on an implementation side, we can then see what is the cost of converting things to a canonical form. All right, so let's look at the variables. So I want to show that it's sufficient to assume that the variables are non-negative. So we can look at some subcases. Subcase 1, there exists let's say t, such that xi is greater than or equal to t. And maybe t is negative. How could we handle this? What kind of new variable could we use that would convert it to being greater than or equal to 0? What new variable should we study? Yes?
U xi plus t.
Yeah, xi minus t. So let yi be xi minus t, and now you get yi is greater than or equal to 0. And because everything is linear, all this is going to do is it's just going to throw multiples of t onto the other side. So as long as xi is greater than or equal to some finite number, we can easily switch to a new variable that's greater than or equal to 0. At a cost of changing maybe the entries of b. At a cost of maybe changing the objective function by a constant. Well, if I change the objective function by a constant, does it matter? If I'm trying to maximize how much money I have, is that the same as maximizing $100 more than the amount of money I have? Yes. How many of you remember distance maximizations from calculus? Or minimizations? You want to find the point that's closest to a parabola. For some reason you really care about this. Why don't you like minimizing or maximizing distance? Because there's a square root. You don't want to minimize the distance. What do you want to minimize? The square of the distance. And so if you minimize the square of the distance, now the calculus is much, much nicer. All right, so is everybody happy in subcase 1? That there is some t such that xi is greater than or equal to 2. All right, what's the other case? So here we had some finite number such that xi was no smaller than that.
Strictly less than.
I'm sorry?
Strictly less than.
Oh, okay, so now having it as an upper bound. If we had it as an upper bound, we could actually just do it with a negative. So that's a good point. If we had it bounded from above, one thing is we could actually put that as a constraint, that xi is greater than or equal to t. We really care more about the lower bound. but that's a good point to be careful about. So what's the other possibility?
There doesn't exist a t.
There doesn't exist a t. So we just have xi is an I. And the solution is brilliant. We just write xi equals ui minus vi, where ui and vi are greater than or equal to 0. We can write any real number as a difference of two non-negative numbers. If I want to write xi as -5, I can write it as 1 minus 6. I could also write it as 2 minus 7. So one of the problems here is we now have multiple representations of the same number. But this allows us to assume that all of our variables are non-negative. So right now, it's not clear if this is a good idea from an implementation standpoint. From a theoretical standpoint, yes, because now we can always assume our variables are non-negative. Frequently, in a lot of problems, the variables will be non-negative. They're going to represent things such as how much food do you consume, how much do you buy. We will often use binary indicator variables. So frequently, our variables take on the values 0 or 1. It's 1 maybe if we're showing a specific movie on a specific screen at a specific time, or if a flight is leaving a specific city to another city at a specific time. So a lot of times our variables are just 0, 1. This is not really anything we need to worry about. Okay. Any questions about the first part, that we can assume the xi's are greater than or equal to 0? Okay. Let's look at the next part. So the next part is we want to assume that we just have equalities. So 2. So we may take ax equal b. So let's look at a given line. We could have a I1 x1 plus ai2 x2 plus plus ain xn and then vi. And we have several possibilities. I claim, first of all, that we don't need to worry about this being less than or equal to. I can always assume if I want that it's greater than or equal to. Why can I always assume, if I ever had a less than or equal to, how can I change the less than or equal to a greater than or equal to?
Well, I was going to say that you could add bi to all the x's, but I don't think that's correct.
No, because we don't know what the x's are. So if I have that this is less than or equal to, I can change my matrix such that this now becomes a greater than or equal to.
Multiply by negative.
Yeah, I can multiply all the a's by -1.
Yeah.
So if you have less than or equal to, multiply all aij by -1. So we just work in one row at a time. So if we ever had a less than or equal to, we can make it a greater than or equal to. If we ever had a less than, we can make it a greater than. So this breaks us down into, there's really only a couple of cases. We have greater than equal to, or equal to. We can get rid of all the other cases. Okay? So what we want to do is we want to show that it's enough to just consider the case where we have equality. Any thoughts about how we would change things to have equality? Remember, our matrix is constantly changing. Our variable list is constantly changing. I'm not saying at the end of the day we have the same variables and the same constraints as we started with. I'm just saying there's a new set of variables and a new set of constraints that will code the same problem. Any thoughts as to how we can get it to the point where it's an equality? We need to somehow change either the variables or the constraints aij. Yes?
What if we subtract a constant amount from every term in the row, such that it now sums up to vi?
Okay, so are you doing it by adding a variable or by changing the a's? You can only do one or the other.
I think by I'm not sure actually.
So this is what we have. And let's say this was strictly greater than vi. Okay, I want to make it equal. If I subtract, let's call it, zi. We'll use a new letter. And let's assume zi is greater than equal to 0. I can subtract enough to make this a strict equality. If, let's say this was 5 more than vi, it needs to be greater than to satisfy the constraint set. If this is 5 more, well, I now subtract 5 and now I have an equality. So I can go from a greater than to an equality. I can go from a greater than or equal to by just subtracting an appropriate amount. So again, let's say we started off with a greater than, and the left-hand side was maybe 15, and the right-hand side, the b, was 10. This would be a fine constraint. This would be valid. This would be feasible. It satisfies the constraint. Left-hand side is 15, right-hand side is 10. If I now subtract 5, it now becomes an equality. So by introducing a new variable, a new slack variable, I can make the two sides equal. You have to ask yourself, is this worth doing? We've now introduced a lot more variables, potentially one more variable for every row of our matrix. But now we no longer have inequalities. We now have equalities to work with. And there's a hope that this is a good idea. So any questions about this? Is everybody comfortable that we can add slack variables and now make all of the rows equalities? Yes?
I'm just not understanding how the left-hand side is a function of x and subtracting a constant to make it equal to something.
I'm not subtracting a constant. Zi is a variable. This is a new variable. That's why I put zi is greater than or equal to 0. We're expanding our list of variables by 1.
Does zi depend on x also?
Well, if we want this to be satisfied, then the value of zi is going to depend on the values of x's with the dot product here and the values of b. So in fact, zi is determined. It's going to just be this dot product minus vi. So zi is forced upon us. Now we've got to be a little bit careful here. Do we know for sure that zi is going to be greater than or equal to 0? Yes?
Yes, because we've changed it to only greater than or greater than equal to. So the dot product minus vi should always be.
Okay. So we wanted this to be greater than. So since we want this to be greater than, we'll know zi has to be greater than or equal to 0. So we don't have to worry about that. If by chance zi was not greater than or equal to 0, if zi was just real, we would still know how to handle that as well. But we can assume that zi is greater than or equal to 0 because we want this left-hand side to be at least as large as the right-hand side. This is a very expensive class. We are adding a lot of variables. But we now have one form, and just from a theoretical perspective, if we want to prove convergence theorems or whatnot, it's very nice to say we're always working with equalities. Okay. Everybody comfortable with this so far? The last one is the easiest. And so I wrote down that we want to minimize. Okay? How many of you are thinking of going into finance? Okay. You probably do not want to be thinking about minimizing return. Okay? Your bosses will not be happy if you show them how to minimize the return on their portfolio. Right? What would you like to do? Maximize. So we have a method, let's say we have this beautiful black box that will solve the canonical linear programming problem and will minimize your return. I don't know if the following is true. It is almost surely an apocryphal story, but I find it amusing and I find it worth telling. Do you remember we talked a little bit about how to find maximum and minimum in calculus? And so there's the story that they were trying to develop one of the stealth fighters or stealth bombers. So what are you trying to do? minimize detection, maximize stealthiness, whatever way you want to put it. And the story goes they didn't check to see if they were at a maximum or minimum, they just checked to see if they were at a critical point. And so for one of the things, they did not have the stealth minimization, they actually had the maximization, the I'm here plenty. Okay, it's probably not true. But it's amusing to think that they didn't check, and what they were building is this thing that's going to say, here I am, I'm coming. Okay, so let's say you want to maximize return and not minimize, but you only have a procedure that minimizes. How can you convert maximizing to minimizing? So it's enough to minimize. So how can you convert, yes? Multiply by -1. If you want to maximize, multiply by -1. So maximizing C transpose X is the same as minimizing negative C transpose times X, or dot with X. So it really doesn't matter if you want to talk about maximizing or minimizing. They're essentially the same after simple multiplication. Okay? So we can now convert any linear programming problem to something of this form. Okay. Any questions on what we've done so far? Okay. All good? So we can now always assume we have something of this form. And then the question will be, how will we solve this? So the goal is to solve efficiently. It is not enough to solve problems. We want to solve problems well. All right? As an example, I'm going to give a subtraction problem right now, and I'm just curious to see who can solve it first. 31 minus 2, 141 minus 31, 199 minus 141, 2011 minus 199, 2016 minus 2011. What's the answer? What's the answer? This is taking too long. I'm sorry, 2014. So why is the answer 2014? It's telescoping. Cancel, 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 cancel. Right? One way to solve this problem is 31 minus 2, that's 29. 141 minus 31 is 110. Dot, 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 dot. Solve all these subsequent problems and then add them. A faster way is to just notice a lot of these internal calculations cancel. And the goal is to get to the answer. You should have seen telescoping sums at least once in your math career. Where have you seen telescoping sums? Anybody remember where you've seen telescoping sums? Yes?
Just like converging series.
Well, in which converging series? An extremely important theorem in mathematics. Part of this class is a chance to go back and show you some of the other math you have either seen or hopefully should have seen in your careers, and just give you a unified appreciation of what we're doing to you as math majors or stats majors who are grading this class. Anybody know where you've actually seen telescoping sums? Why might we care about telescoping sums? Yes?
Was it alternating?
Something similar to the alternating harmonic has a telescoping sum, and in fact we talked about something like that in Math Puzzle Night. But this is not a truly important theorem. There aren't that many fundamental theorems that you've seen. right? Fundamental theorem of calculus. The only other ones you may have seen is the fundamental theorem of arithmetic. You might have seen the fundamental theorem of algebra. So fundamental theorem of arithmetic is on every number can be written uniquely as a product of primes if you write the primes in increasing order. Fundamental theorem of algebra, polynomial of degree n has n roots. There is the fundamental theorem of linear algebra, which I do not believe deserves the fundamental status, but a lot of people, are kind and give it to that. Has anyone seen any other fundamental theorems? We don't bandy the word fundamental lightly. Right? You've got to be truly important to have the fundamental designation. Fundamental theorem of calculus. The way you prove the fundamental theorem of calculus is standard argument is with telescoping series. How many of you have seen a proof of the fundamental theorem of calculus? Oh dear Lord.
Maybe.
Oh my God. And this is on tape. Okay. Quick detour. You cannot graduate as math majors without seeing the fundamental theorem of calculus proof. We've got 6 minutes left. Proof of fundamental theorem of calculus. Let's see. All right. So here's 0, 1. Without loss of generality, I've only got about 6 minutes. I'm going to assume my interval is 0, 1. If I can do it for 0, 1, I can do it in general. I'm going to partition, here's xi, here's xi, well, it's double x, xi plus 1, and the gap between these is going to be 1 over n. Okay? And what I want to do is I want to find the area under the curve. And so what I can do on each of these intervals is I want to approximate the area under the curve. And what we typically do is we find some point where the function is smallest, call that Li, and we find some point where the function is largest, call that Ui for lowest sum and upper sum. And we get the upper sum approximation, and we get the lowest sum approximation. And the goal is to show that this converges. All right. And so how do we do this? So the area satisfies the following. We write the area as the integral from 0 to 1 of f of x dx. That's just our notation for the area. This will be less equal to the sum. I goes from 0 to n minus 1 of the upper value times 1 over n. And it will be greater than or equal to the sum I goes from 0 to n minus 1 of f at the lower value times 1 over n. So if we subtract, we want to show that these two numbers are converging to a common value, and that common value is the area. So we want to show the distance between these two goes to 0. So the distance is the sum I goes from 0 to n minus 1 of f of ui minus f of li times 1 over n. If you've done real analysis, you know we have a continuous function, and we can choose the partition so small that this distance is at most epsilon. And so if we use some results from real analysis, this is going to be less than epsilon over n, which will go to 0. If you don't want to do that, if we assume f prime is continuous and bounded, then we can use the mean value theorem. And the mean value theorem would say that this is going to be less than or equal to the sum I goes from 0 to n minus 1, f prime at some point ci in absolute value, times the distance between ui and li. How far apart can ui and li be? What's the furthest apart ui and li could be?
Xi plus 1 is xi.
Right, how far are these? They're just 1 over n. So we would get 1 over n, and we would have a 1 over n from this. We have n terms, and if we assume that this is bounded by, say, b, this would be less than or equal to b over n, which will tend to 0. So we don't need the assumption that f prime is continuous and bounded, but it means I don't have to use real analysis. Okay? So this tells us that the upper and the lower sums converge to a common value. And that common value, it has no choice. It has to be the area. Okay? Everybody happy with part one? Part two is, this is just a definition. I'm just using this as the definition of the area. I want to show that this really is the antiderivative. All right, so we've got about 4 minutes left, not even close. All right. So let's see. So, how many of you have ever watched the TV show Friends? Except for, I think, maybe the first episode and the last episode, what does every episode of Friends title begin with?
The one.
The one with. So when I teach this as a calculus class, this is the one with the mean value theorem. When in doubt, use the mean value theorem. The mean value theorem is one of the greatest results in calculus. It's in some sense a poor person's Taylor series. So what I want to do now is I want to somehow show that this is the antiderivative. So let's let big F prime equal little f. So it's some antiderivative. Let's look at big F of x I plus 1 minus big F of xi. By the mean value theorem, this is big F prime at some point, let's call it wi times the distance, which is 1 over n. So I'm applying the mean value theorem to the antiderivative. Okay? So I get big F of xi plus 1 minus big F of xi is little f at some point wi times 1 over n. Question? Okay, so now I sum both sides. Sum I goes from 0 to n minus 1 of f of xi plus 1 minus f of xi is equal to the sum I goes from 0 to n minus 1 of f of wi 1 over n. But let's think of what's going on. Here is f of li. Here's f of ui, and here's f of wi. It has to be at least as large as the smallest value in the interval, and it can't be larger than the largest value. Right? So this is sandwiched between the upper and the lower sums. So it lives between upper and lower. Lives between upper and lower. As n goes to infinity, what does this go to? It goes to, what must this go to as n goes to infinity? Not 0. This lives between the upper and the lower sums. What do the upper and lower sums converge to as n goes to infinity? What are the upper and lower sums converging to? The area. Right? We're using this as the area right now. We don't know that this actually means antiderivative. The upper and the lower sums converge to the area. That quantity always lives between the upper and the lower sums. What must that quantity converge to? Area. It has no choice. It's the sandwich theorem. It goes to area by the sandwich theorem. So this goes to the area. Now the left-hand side, what does this go to as n goes to infinity? What kind of sum is this? Given that this rant was inspired, it's a telescoping sum, right? It's a telescoping sum. All the stuff cancels except the first and the last. And this is always equal to f of xn minus f of x0, which is just f of 1 minus f of 0. The antiderivative at b minus the antiderivative at a. So this quantity converges to the area, and it's always equal to f1 minus f of 0. This quantity is actually not changing. This quantity is always the area. The mean value theorem doesn't tell us where these point wi are, just that they exist. And so it's actually worth a little bit of a detour to see this. This is theoretical math at its greatest. We have some points. We don't need to know where they are. These points exist. And they allow us to get this wonderful result at the end that the area is the antiderivative. So this is one great application of telescoping series. So now you've at least seen a proof of the fundamental theme of calculus. We can check. I don't think we did it in under 5 minutes, but definitely in under 6. All right.